Hi and welcome again to another tutorial, and this is a very interesting one and I'm sure you're gonna enjoy this. I can't stop loving this app, Digital Logic Simulator. Okay, and this is part 3. Remember, in part number 2 we created a D-level sensitive latch, and this is a 3-bit asynchronous up counter. And as you can see, if I tap on this flash icon right here, which is a simulation, the counter actually goes up. So it starts with 0, increments by 1, goes up to 7, and then once it goes to 7, it just goes back to 0. And that's what you see. Also, if you look at the circuits, I got 3 flip-flops there. All of them are JK. The JK are set to 1 through that switch that you see on the left, and the clock is fed into flip-flop A. And because it's an asynchronous, so the output becomes the clock to the following flip-flop. So just to go through a little bit of theory, we're actually going to make this, but just to go a little bit of theory related to 3-bit asynchronous up counter, I'm going to take you to lecture number 17 of the Digital Electronics series, where we actually learned about the property of the JK flip-flop. When both J and K are 1, then your next state is basically the complement of the previous state. Okay, basically it toggles. So if the present state or a previous state is 0, the next state is going to be 1, and this only happens when JK is 1 and clock is high. Okay, so for a 3-bit counter, so say initially the logic is 000, the next logic will be 001, increment by 1, it goes all the way to 2 and 2, 7. Once it reaches 7 right here, it'll go back to 0 here. Okay, now how it works, you have this I have 3 flip-flops right here, and all of them, the inputs are set to 1, as you can see in the red. Also, because it's an asynchronous 3-bit up counter, the output of one flip-flop becomes the clock of the following. Okay, right? Also notice QC here is the most significant bit and QA is the least significant bit. So say if the present state is, say, 001, which makes a code of 1, correct? So the next state is going to be 2, so we would hope that we get 010. Because QB is 0 here and it's fed into this clock, and clock is 0, so QC, it's going to hold on to its previous state. I'm going to change the color here. So it's going to hold on to its previous state, which is going to be 0 now. Okay, QB, because QA is 1 and it's fed into this clock right here, so and because JB and KB both are 1, the next state is going to be the complement of the previous state, and because the previous state was 0, the complement of that is going to be 1. And here you have J and K again both set to 1. When the negative edge of the clock arrives, the output is going to be the complement of the present state, and because the present state is 1, so the complement of that will be 0, so you get 0, 1, 0, and that makes a code of 2. And similarly, if you do that, it will basically keep on incrementing. Here is the timing waveform over here. So just wanted to give you a real theory, a background about that 3-bit asynchronous up counter. Let's now go ahead and make this circuit, which actually this one right here, I'm gonna make exactly as it is, and I'll show you how you can do it. I just can't stop loving this Digital Logic Simulator app, and it's very fancy and it's a very exciting way to learn and implement flip-flops, especially the counters using JK flip-flops. So notice I need 3 JK flip-flops, I need 1 switch, 1 clock, and 1 7 segment. So let's get rolling. You know that you have to hold on to the component for a couple of seconds maybe, or maybe a second, and then drag it into your workspace. So the first thing I'm going to do is going to connect the switch that you see to all the inputs of the flip-flops, and I'm gonna set it to high because J and K, they all need to be high. Also, I'm going to click on this small gear right at the top, the bottom right of the JK flip-flop, and I'm gonna make sure that I am actually choosing the clock. And because it was a negative edge trigger, so I just need to tap on the negative. It's already negative edge, so I'm okay over there. Click OK, and then as you click on the tap on the clock, you see there's extra input that would come here, and all you need to do is actually I'm just gonna hook up my clock. Actually, I'm gonna use a different so if I click on this wire looking thing on the top right here, which is the green icon, and then let's say I want to have my clock in green, so here I come, and then this is my clock. Remember, this right here, the output of this flip-flop becomes, well, I need to make sure it has a clock also, and also this flip-flop. Let's now connect the output of this one to the clock of this, and the output of this flip-flop to the clock as this right here. Okay, you can also hold on to these flip-flops and rearrange them such that it makes sense for you, or it's easy to track wires. And also, if you wish, you can also label them as, if you click on this small gear right here, remember this is my QC, my most significant bit right here, and then also this right here, the top one is my QA, and this is my least significant bit. Okay, I'm gonna click OK. So my most significant bit, also I need to make this wire disconnection right here. Okay, all looks good. All I need to do is connect my most significant bit to here. Okay, my least significant bit goes here, and then the output, this right here, which is QB, goes over here. Okay, so say if you, this is only 3-bit, if you were going to do 4-bit, remember your most significant bit will go at the top right here. Okay, and because I only had like 3 bits, so I'm gonna use the second, which from the top, that would be my most significant bit, and the bottom green dot that you see is the represents the least significant bit. So now let's run the simulation. Here we have been able to replicate the exact circuit that we had over here, this right here, and hope that this will basically work as a 3-bit counter, starting with 0, goes all the way to 7. Okay, so let's get rolling. Let's see. I'm gonna click on this flash looking icon on the top left, and then I'm gonna turn my clock on. Also, I'm gonna turn my switch on, and you see the timer is working. It's basically not a timer, it's a counter. Could be a timer also. Also notice if I click on this gear right next to the clock, I can set the frequency. Right now it's set to 1 Hertz, so it's changing every 1 second. So if you want to say every 2 seconds and then click OK, and then you do the simulation, the counter then moves up every 2 seconds. And also, if I look at the timeline here at the bottom, you should be able to see the waveform here also. Now, what you see, the timing waveform, is the waveform for the counter that you see with the purple background. This one, if you want to look at the timing waveform for the circuit that I just created, all you need to do is you have to tap on this black dot right here, okay, and then put a check on monitor. Similarly, I'm going to do it for at the output of each flip-flop, here too, and then here too. There you go. And then when I run the timeline, if I go to the bottom, you see at the bottom I have my QC, which is the most significant bit, then I have my QA, which is the least significant bit, and this JFKKG is the middle one, okay, which is basically QB. So if I pause this right here, notice here I got 0, 1, 0, 1, 1. So the next would be 1, 0, 0, right? Here you go. Here is your 3-bit asynchronous up counter. I hope you enjoyed this this video. Again, you know, this is so easy, so fancy, and you know, on your fingertips you can actually just create flip-flops and then create counters out of them, especially when you do JKFlipFlops. I hope you enjoyed the video. Don't forget to subscribe to the channel if you haven't already, and I shall be back with another one. Stay tuned.